Okay, so now this is an iron core. And what that does is it just helps strengthen and direct the magnetic field. So what I want to do is take this ring. This is an aluminum ring. It's a pretty good conductor. So I've basically got a loop of wire. And that loop of wire is going to be sitting on here. We're going to have a changing magnetic field. The changing magnetic field creates a current. A current creates a magnetic field. And those magnetic fields always oppose each other. Let's see what happens. What's going to happen to my ring? It's going to jump, isn't it? You ready? 3, 2, 1. Okay? Jumping, I'm going to turn this way. So it jumps toward me. There we go. Okay? So what I want to do is to try to show you that the reason that's jumping is because we're getting current here. And that current is acting like a magnet in the opposite direction. And how do I do that? Well, I've got another ring. And this ring, I took a saw to it, and I cut a slot in it. Let's see if we can see that. Okay, this one has a slot cut in it. And so it does not form a closed loop. It cannot generate a current because there's not a closed path there. So I put it on here, and I turn it on. Nothing happens. How'd you know I turned it on? I can be tricky, you know. How about this? I'll put this ring on top. Okay, you ready? Okay, so this one jumped. This one didn't. It's the current forms a magnetic field, and they interact like that. Yes, it has to be a closed circuit. Perfect. So I want you to just get a quick look here at how high this is going. Because the story is not as simple as I made it out to sound here. I said we've got materials that conduct electricity, right? That charges can move through them. And we've got insulators. We've got materials that don't conduct. Charges can't move in them. Actually, it's not one or the other. It can be kind of in between. It can be a really, really good conductor and charges move really easily. And it can be not such a good conductor and charges move, but not very well. And so if this was a better conductor, we would expect to get more current. More current, we would expect more magnetic field. More magnetic field, we'd expect this to jump higher. So let's see if we can make this a better conductor. And we're going to do that by making it really, really cold. Most metals, if you make them cold, they become better conductors. So let's watch how high it's jumping. It's pretty consistent, right? Okay, pretty consistent. Got the idea of how high it jumps? We're going to make it cold. We're going to do that with liquid nitrogen. I'm going to put my ring in the bucket. Pour a little liquid nitrogen in there. Liquid nitrogen is pretty close to negative 200 degrees Celsius. So it's cold. Now I'm going to put on my special glove. Because when you touch something that's really, really cold, it's kind of like touching something that's really, really hot. It damages your skin. It hurts you. So I need to protect myself. In fact, when this ring jumps, I'm going to try to catch it. But with this clumsy glove, it's a little hard to catch. If I miss the catch and it rolls off the stage, don't touch it. Okay? There's a reason I'm wearing this glove. Okay, let's see. You remember how high it was going before? Okay. So let's put it on here now, and we're hoping it goes higher. You ready? 3, 2, 1. One more time. 3, 2, 1. Okay, so it goes a lot higher, right? And that's because it's a better conductor. It's colder. So let's do a little recap of what we learned about here, electricity. We started out talking about static charge, right? Sliding out of your car touching the door, getting a shock, kind of dragging your feet as you walk across the carpet and going to touch the doorknob, you get a shock. This little girl sliding down one of those plastic slides at the park, building up some static charge, right? This has happened to us, right? Static electricity. We talked about the Faraday cage, right? The metal, the conductive cage that protects things from electric fields. You might think to yourself, well, when am I ever going to see one of those? It turns out I was driving down Highway 680, and there's a new carpool lane there. And if you have a carpool, if you have a passenger in the car, it's free. You can use that carpool lane. If you don't have a passenger, if you're driving by yourself, you can pay money to use the lane. And you pay with your Fast Pass. But whenever you drive into that lane, your Fast Pass gets charged. Your Fast Pass doesn't know whether you have a passenger in the seat with you or not. So you check the Fast Track website, and it tells you to take your Fast Track and you put it in the conductive bag that was shipped with it, seal it up in there, and it won't get charged. It's a little Faraday cage to protect it. And electricity is just all around us, isn't it? You walk into your kitchen, your refrigerator, your toaster, your cappuccino machine, they all plug in, right? And think about all the things that don't plug in, all the things that have batteries, all the electrical devices we have. In fact, electricity is such an important part of our cars, our trains, our planes. If you wanted to go visit your friend, you couldn't do it without electricity. You might think, I'll just call them. Not without electricity. Your voice is converted into sound, into electrical signals, and then it's converted back into sound. You might think, oh, I'm just going to walk to see them. Not without electricity, because your muscles, it's electrical signals in your body that make those muscles contract. You can't see without electricity. You can't think without electricity. It's electrical signals in your brain that make your thoughts. In fact, even with electricity, some of us have a hard time thinking, don't we? It's all around us, and because it's all around us, we've got to generate it, right? We've got to make it happen. And on a large scale, it almost always happens the way Lauren demonstrated, turning that loop of wire in a magnetic field. We can burn oil or coal. It boils water. The steam turns a coil of wire in a magnetic field. We can use water to turn a coil of wire in a magnetic field. We can use wind to turn a coil of wire in a magnetic field. This is the world's largest solar power plant in the Mojave Desert in Southern California. These are mirrors. They're reflecting the light to this centered part of the tower here. And it's heating up a liquid that's boiling water, that's generating steam, that's turning a coil of wire in a magnetic field, right? So on a large scale, that's how we do it. Now when you see solar panels on people's houses, that works very differently. But on a large scale, we generate electricity with what we showed you here today. The physics of electricity all around us in our everyday lives. We want to switch gears, but before we switch gears, we should probably point out that electricity, because our bodies use so many electrical signals, electricity can be very, very dangerous for us. And so it looks like we're having fun, we're touching electricity, but we are very careful. We know what we can touch and what we can't touch, right? This sign over here, nobody touched that. That can be very dangerous. The Jacob's ladder, nobody touched that. The Van de Graaff is much safer. We can touch that and play with that. We know that. But at home, you have to be very careful. Don't ever touch things that plug into the wall if they're open, right? If you can get your hands inside, don't touch them. Be careful with electricity. It can be very dangerous. Okay, temperature. We're going to start off temperature the same way we started off electricity. Everything is made up of atoms. And atoms are teensy tiny little things. If you started taking some atoms and stacking them one on top of the other, 5, 50, 500, 5,000, 500,000 stacked, 500,000 atoms, one on top of the other, it would be the thickness of a sheet of paper. Okay? These are teensy tiny things. And we can't see them with the world's most powerful optical microscope. We need a special kind of microscope. We need an electron microscope to see atoms. They are tiny, tiny things. But everything is made up of atoms. And so, what does temperature tell us? It tells us how fast they're moving. It tells us how much energy they have. So, when you kids are out on the playground, and some of you are running around really fast, and some of you are standing still, who has more energy? The kids running around, right? And when some of you are running around really fast, and some of you are standing still, who gets hotter? Running around. And which ones? The kids that are running around? Or the kids that are standing still? Which ones take up more space? The kids running around take up more space on the playground. It's the same with physics students and physics instructors. It's the same with atoms and molecules. The ones that have more energy move faster, they're hotter. We can take their temperature. We can tell how fast they're moving, how much energy they have. And so things, when they heat up, they tend to take up more space. It's kind of like people on a dance floor. You put a bunch of people on a dance floor, and they're not moving very fast, you can have them all dancing there. But they start really moving and jumping around, you need a bigger dance floor, right, to accommodate them. Let's see what happens when we heat up a solid.
So this wire is the same type of wire as in your toaster at home. When you run a current through it, it gets really, really hot. Now here we have a weight in the middle of the wire, 4 pieces of paper, and some tape to mark where the wire started. Let's see what happens when we run a current through this wire. Is this wire longer than when we started? Started up here, now it's down there. That's right. So how do you tell if it really is hot? Could touch it. Let's crank this up a bit higher. Now that I've turned the current off, let's see what happens to the wire. And remember, those pieces of tape mark where it originally started. Now as this wire cools back to room temperature, it will eventually return to these white tape marks and back to its original length. So with this wire, what we see is the thermal expansion of a solid. Let's go over to Frank to see what happens to a gas.